Hi everyone, I'm Akshay Pratinav from Intuit. Today I want to talk about a topic that most of us only think about when things are already going wrong, that is regional failover. Specifically, how failover becomes exponentially harder in modern microservice architectures, where you are not just dealing with stateless APIs, but databases, async pipelines, batch jobs, and routing layers, all of which behave very differently during failure. This talk isn't about a specific product or tool, it's about patterns we learned while trying to make failover predictable and ideally boring. Here is a high level agenda. We'll go over problem statement and motivation. Then we will align on few principles and mental model. Then we are going to talk about platform architecture, outcomes, and key takeaways. Before we go into architecture or solution, I want to level set on the problem we are actually trying to solve. By now, I think we can all agree on one thing: outages are normal. Cloud regions fail, managed services have bad days. Even highly reliable systems eventually hit failure modes they didn't anticipate. What really hurts business and customer isn't the outage itself, it's the recovery. When recovery is slow, manual, and chaotic, customer trust erodes quickly. So the real question isn't how do we prevent outages? It's how do we recover in a predictable way? Microservices gave us a scale and velocity, but they also changed the failure landscape. During a regional outage, you're not just failing over one thing. APIs might come up quickly, but background workers may lag. Databases may need promotion. Async pipelines may replay or stall. And all of these components have a different recovery characteristics. The key lesson we learned is this: your system only recovers as fast as the slowest workload in the stack. So, when we look at the major incidents, the outage itself is rarely the most damaging part. What actually determines customer impact is how quickly and predictably the system recovers. And under pressure, humans become the weakest link. Not because they are bad engineers, but because the stress, fatigue, and incomplete information lead to mistakes. This is why automation and standardization matter so much in disaster recovery. In many organizations, evolves organically. Each team builds what they think is good enough for their service. Over time, you end up with dozens or hundreds of different DR strategies. The problem isn't that these solutions are bad individually. The problem is that they don't compose. During a real outage, fragmentation turns into confusion, and confusion turns into delay. So, runbooks are often treated as a safety net, but during a real outage, engineers are context switching, debugging incomplete signals, and coordinating across teams. That's a terrible time to follow a multi page checklist. The more your recovery depends on human memory, the less reliable it becomes, especially at scale. Now that we have talked about the problem, I want to go over a few principles that went into building disaster recovery platform. When we say boring failover, we are not minimizing its importance. We mean that failure should be so predictable and well rehearsed that it doesn't require heroics. No one should be scrambling for runbooks. No one should be manually scaling clusters at 3 a.m. Boring failover is a sign of engineering maturity. One of the design principles is declarative intent. The biggest shift we made was moving from imperative procedures to declarative intent. Instead of telling teams how to fail over, we ask them to declare what they need: capacity, dependencies, data requirements, and criticality. The platform then owns the mechanics. This removes a huge cognitive burden from service teams and creates consistency across the organization. Another design principle is to fail over the entire stack. A partial failover is usually worse than no failover. If your API fails over but your async workers don't, you can corrupt state or build up massive backlogs. We learned that failover has to be treated as a full stack event, that is, compute, async workload, data, and routing layer executed in a coordinated way. Anything less creates hidden risk. Remember that failover is not a point solution, it needs to be end to end. So, standardization doesn't mean treating every workload the same. A customer facing API has very different recovery requirement than a nightly batch job. The key is providing a common framework where services can express those differences declaratively. The platform adapts behavior without teams reinventing the wheel. Another design principle is pre-scale capacity. Another major source of downtime is cold capacity in the secondary region. Instead of guessing how much capacity we might need, we pre-scale based on live traffic patterns from the primary region. That way, when failover happens, capacity is already there. Now, recovery becomes more about traffic movement, not infrastructure readiness. Compute can usually be restarted. Data is where things get dangerous. Promoting a database or cache involves consistency, ordering, and correctness guarantee. Automation here isn't about speed alone, it's about safety. By encoding these steps into the platform, we reduce the risk of human error during high stress incidents. Traffic routing is often treated as the final step, but it's actually a core control mechanism. Whether you use DNS or a service mesh, traffic should move based on health signals, not manual decisions. This makes failover observable, reversible, and far less risky. Traffic routing becomes part of the system, not an emergency lever. One mistake we often see is treating failover like a switch. In reality, it's a workflow. You scale, promote, validate health, shift traffic, and verify things. Skipping steps is how incidents turn into big outages. Remember that toggles don't recover systems, but workflows do. So, up to this point, we have talked about problems and principles. Now, I want to ground these ideas in a concrete system. So, let's look at DR procedure YAML example for an active passive microservice that uses a database. So, in this example, we have 4 stages. So, stage 1, as you can see, is a prescale east stage that basically prescales Kubernetes pod in the failover region and matches the capacity with existing region. This is done by updating HPM and replica value. Stage 2 is promoting database to primary in failover region. Stage 3 is about dialing traffic in failover region. And the last stage is stage 4, which is resetting HPM and replica value to original value so that teams don't pay for extra compute cost after traffic reduces. All these stages run in a sequence, that is, stage 2 starts after stage 1, has completed, and so on. So let's take a look at high-level architecture. So here there's a user who is executing a DR plan using UI. And this DR plan has 3 stages, that is prescale, dial, and reset. It sends requests to the backend API. Backend API starts state machine. State machine sends event to Kafka topic. As you can see on the screen, prescale stage has been sent to Kafka topic. We have different agents like database agent that performs failover operation on a database. Then we have capacity agent that analyzes compute capacity and performs scaling operation. After agent receives event in Kafka topic, the right agent picks the task or the stage and it creates a lock in semaphore service. Now state machine polls for semaphore service lock status. Only after semaphore is unlocked, it sends the next stage to Kafka topic. Ensuring consistent execution of stages in the expected order. So on every Kubernetes cluster, there is in-cluster add-on running that pre-scales pod on receiving pre-scaling requests. Those agents also rely on external monitoring tool to verify status of every action. For example, after pods have pre-scaled, metrics in monitoring tool should reflect that information. This gives an indication for agent to unlock semaphore so that state machine can safely proceed to next stage. As you can see, platform has both front-end and back-end component. Front-end component is built using React, and for back-end component, we are using Golang and Python. Let's go over safety and operation that turns a fast failover into a reliable one. So speed alone isn't the goal. Fast but unsafe failover can be worse than staying down. Guardrails like health gate, dependency validation, they ensure we only move traffic when the system is actually ready. And equally important, every step is reversible. So automation only works if the system is ready. That means requiring health gate, dependency check, and drift detection. We must eliminate DR-only config. No special flags you flip once a year. Production should always be failover ready. Failover shouldn't depend on hope. Regular game days completely changed how teams think about failover. Because it's automated and standardized, drills are low stress and repeatable. The first time you fail over should never be during a real outage. So to wrap things up, I want to step back and talk about outcomes and takeaways. So anti-patterns to avoid include ad hoc scripts. Ad hoc DR solutions don't usually fail during design. They fail during execution. Inconsistency, cognitive overload, and untested assumptions show up at the worst possible time. Standardization isn't about control, it's about safety. So when failures is standardized, a few things happen. Recovery gets faster, operational overhead drops, teams spend less time preparing for disasters and more time building features. Most importantly, incidents become manageable instead of chaotic. So, one unexpected benefit of standardizing failover was the cultural shift it created. When engineers trust the system, they are more willing to practice, experiment, and improve it. So, failure stops being something people fear and starts being something they understand. That confidence compounds over time. If there's one message to take away, it's this: standardize failover across all workloads and use declarative intent. Also, pre-scale capacity intelligently and practice regularly. Boring failover is a key sign of a mature system. Thank you, everyone. Feel free to connect with me via email or LinkedIn if you have any questions.